This video talks about the second mode of operation for timers in the AVR microcontroller. And this mode is maybe a little bit more intuitive or straightforward. This is called CTC for Clear Timer and Compare Match mode. And in this mode, the counter goes up until it matches a value that's set by the user. And that value is stored in the OCR, or output compare register, for timer 0. So for timer 0, it's OCR 0. And this is another plot showing the counter register as a function of time. And you see here it starts at 0 and goes up until it gets to this value, which is OCR 0, whatever we stored in OCR 0. And then after that, it drops down and goes back to 0. And whenever that happens, just like in normal mode, whenever it reached 255 and went back down to 0, then the overflow flag was set. Well, in CTC mode, it'll go up to whenever it matches this value, and then on the next cycle, it'll go to 0, and the output compare flag is set. So you can see here the counter is going up, and it's about to match. Okay. And then that flag stays set until you reset it, either by writing to it, or if you're using an interrupt, then it's handled automatically. But we'll talk about interrupts later. So for our examples, we're going to clear that flag by writing a 1 to it. We want to redo the example that we had before, but now we're going to use CTC mode for the timer. So things that'll change are going to be that the timer counter control register is going to be different. Remember, the WGM bits determine whether it's in normal mode or CTC mode. And then we're not going to write to the TC&T0 register. Instead, we're going to write to the OCR0 register. So here we go. We're still using the output pen, port B, pen 5. Here we've written 250 to output compare register 0, and we've put a different value to OCR0. So B in hex is 1011. So 01 for the WGM bits makes that CTC mode, and then 011 for the clock selection bits makes it a prescaler of 64. So you remember 250 cycles at 8 megahertz over 64 is equal to 2 milliseconds. So now one other difference is that instead of polling the TOV0 flag, now we're polling the OCF0 flag. And we're left shifting this by the value that the compiler has stored for OCF0 for this microcontroller, which is 1. So this is equivalent to 1 left shifted 1. And that is the example. I guess one other thing different is that we didn't stop the clock in this example, whereas previously we'd stopped the clock. We had this timer counter control register assignment inside the while loop. But the big differences are that we're writing to OCR0 instead of TC&T0. We have a different value for TCCR0. And also we're looking at a different flag now because it's in CTC mode. So question. Again, which register holds the TOV0 and TOV1? Okay. We already did this in the previous video. So I guess the difference is if we have a 1 megahertz crystal, find the OCR0 value needed to generate a 0.2 millisecond time delay. Use CTC mode and no prescaler mode. So let's see. I will get a camera up. Okay, so F is 1 megahertz. The delay is 0.2 milliseconds. and we want to know what value we need to write to OCR0. So that value is the number of pulses, and that's the delay divided by divided by the period. So period is 1 over f, so that's 1 microsecond. Okay, so this is 0.2 times 10 to the minus 3 divided by 1 times 10 to the minus 6. And so that's equal to 200. So 200 pulses. So OCR0 equals 200 is what we need to write in order to get a 0.2 millisecond delay. So here's another example. We want to write a program that toggles port D pin 0, so we're just toggling a pin, every 12.8 milliseconds. And we're assuming an 8 megahertz clock frequency. So the steps are, we need to figure out what values to write. Well, we need to figure out if we need a prescaler first, because the prescaler will help us determine what to write for the clock selection bits. And then we can write, we know what to write to timer counter control register. And also when we know the prescaler and our delay, then we know the number of pulses that we have to count, and that'll tell us what to write to the output compare register. So, bring up that camera again. Okay. So for this example, we have an 8 megahertz clock. So we'll say T0, this would be the nominal period, is 1 over 8 times 10 to the 6th. 0.125 microseconds. And we know the biggest delay we can get from that, 256 times this value is 64 microseconds. Wait, that's not right. Yes, that's 32 microseconds. Yeah, 32 microseconds. Oops, I said that wrong in the previous video. Okay, so the biggest delay we could get from an 8-bit timer with no prescaler would be 32 microseconds, because if we have this much time between each increment, 256 increments takes 32 microseconds. And that is insufficient for this 12.8 millisecond delay that we want. So we need a prescaler. So the prescaler has to be bigger than our delay divided by 256 times T0. Okay. And so that is 12.8 times 10 to the minus 3 divided by 256 times 0.125 times 10 to the minus 6. And okay, so we have, yeah, I don't know what that value is. Hopefully I'll remember to go back and edit this part out. But in case I don't, just bear with me while I get out my calculator. Although, yeah. Calculator. So we have 12.8 times 8 divided by 256 is 0.4, and then we're multiplying that by 1,000. Yeah, so I believe that's 400. So this value here is 400. Because we have 12.8 times 8, and then that product divided by 256, and then multiplied by 1,000 gives us 400. Okay, so the prescaler has to be greater than or equal to 400. And from our choices here, prescaler values, we need to choose 1024, because prescaler has to be at least this big. So prescaler equals 1024. And now our new period, T1024 we'll call it, is equal to 1024 times T0. That's 1024. That happens. Okay. Which is 128 microseconds. And now the number of pulses is the delay over T1024, since we're using a prescaler. And so that is 12.8 times 10 to the minus 3 divided by 128 times 10 to the minus 6. And what is that, 100? Yes, so it's 100. So we need to write 100 to OCR 0. And now that we know the value, we also need to know what to put in TCCR 0. So this right here is a previous example for just a template. So we also need to figure out what to write for TCCR 0. So let me bring up that camera again. Okay, TCCR 0. We have 8 bits to write. And I'll just write in binary. The 7th bit, FOC 0, we're not going to worry about. That's always 0 for us. WGM 0, 0, and 0, 1. This is 0, 0 for normal mode and 0, 1 for CTC mode. So we want a 0 there. The next two are zeros always. And then we want a 1 for CTC mode. And then our clock selection bits. We need a 1024 prescaler. So that's 101. So 101. So that's what TCCR0 needs to be. And that is in hex 0 and D, 0D. Right. And so that was working with the timer and CTC mode. Slide up here sort of is the main one for seeing the difference between CTC mode and normal mode. So in CTC mode, the timer is going to count up until it matches the value in the output compare register. And then once that happens, it'll drop back to 0 and set the output compare flag. And timers and counters are very useful for a lot of purposes, generating regular actions, generating pulse width modulation output, and we will use them in the laboratory experiments that you're going to be doing, or the laboratory exercises.